You've probably noticed it, right? The voice on your phone, your smart speaker, it's gone from sounding kind of clunky and robotic to something that's, well, almost spookily human. But how did that happen? How does a machine actually learn not just to say words, but to speak, with rhythm and tone and emotion? Today, we're going to break down the revolutionary AI leap that finally gave technology a truly natural-sounding voice.
I mean, think about it. You're getting directions on the road. It's reading a text from a friend, or you're just asking about the weather. These voices, they've become a totally seamless part of our daily lives. We barely even think about them anymore.
So here's the real challenge. How do you take silent, written text on a screen and turn it into this, a complex, messy, raw audio waveform? This is one of the hardest problems in AI, honestly, because a single second of sound is just packed with an incredible amount of information.
And this whole idea, it's not new. The ambition to create artificial speech is actually a story of human ingenuity that goes back over 2.5 centuries.
It all kicked off with mechanical bellows and reeds way back in 1791. Then came the first electronic voice at the 1939 World's Fair. And of course, in the 80s, we got the iconic digital voice of Deck Talk, which many of us probably recognize as the voice of Stephen Hawking. But the real game changer, the leap to what we hear today, that happened in the last decade with the AI revolution.
So what was the big shift? Well, the old way was called concatenative synthesis. Think of it like making a ransom note, but with sound. You've got this huge library of tiny pre-recorded audio snippets and you stitch them together. It kind of worked, but it always sounded a little choppy, a little off. The new way, generative synthesis, is a whole different ballgame. It's like an artist painting with sound, creating the audio from scratch, one microscopic sample at a time.
And the model that truly perfected this new, generative approach was a massive breakthrough from Google's DeepMind called WaveNet. This thing didn't just improve on the old methods, it threw out the old rulebook and wrote a completely new one for creating synthetic sound.
Okay, so the magic behind WaveNet is something called an autoregressive model. I know, that sounds super technical, right? But the idea is actually pretty simple. It just means that to figure out what the next tiny piece of sound should be, the model looks at all the little pieces that came right before it. It literally builds the sound step by step, making sure it all flows together naturally.
And when I say step by step, I really, really mean it. WaveNet doesn't think in words or even parts of words. Nope, it generates the actual raw audio waveform itself, making a brand new prediction more than 16,000 times for just 1 second of audio. That's the mind-boggling level of detail you need to sound truly human.
So how on earth does it look back far enough to understand context without just grinding to a halt? The secret sauce is this really clever technique called dilated causal convolutions. Causal is the easy part. It just means it can't cheat by looking into the future. But dilation? That's the magic trick. Imagine trying to understand a sentence by looking at one letter at a time. You'd lose the plot. Dilation lets the network skip ahead. It glances at samples from way back, giving it the long-term context it needs without getting bogged down in every single little detail along the way.
Now, here's a common misconception. It's easy to think that WaveNet does the whole job by itself. But in reality, it's just one absolutely crucial part of a much bigger assembly line, which we call a TTS pipeline.
So let's walk through that pipeline. First, the text gets cleaned up. May 12th becomes May 12th. Simple enough. Then, words are broken down into their basic phonetic sounds. After that, a different AI model turns those sounds into a kind of musical score for speech called a spectrogram. And then, right at the very end, for the grand finale, that's where WaveNet steps in. It acts like a master audio engineer, taking that score and meticulously crafting the final high-fidelity audio that you actually hear.
But there was a huge problem, a massive catch. This sample-by-sample method, while it produced unbelievable quality, was painfully slow. So slow, in fact, that it was completely useless for any kind of real-world, real-time app.
And hey, don't just take my word for it. The researchers themselves put it right in their paper. They said because it was generating audio one sample at a time, it was hard to deploy in a real-time production setting. They had basically created the world's most realistic synthetic voice, but you'd have to wait forever to hear it speak. Not ideal.
So, they needed another breakthrough. And the solution they came up with was just as elegant as the original idea. The logic was, if you can't make the original model faster, why not just train a brand new, super fast model to perfectly mimic it?
This led to a really cool technique called probability density distillation, which uses what they call a teacher-student model. You have the original, slow but masterful WaveNet acting as the teacher. Here's how it works.
You create a new, much faster student network that can generate a whole bunch of audio all at once. Now, at first, its output is just garbage, complete noise. But the expert teacher network listens in, and for every sound the student makes, the teacher gives it feedback. It scores it, telling it exactly how to adjust to sound more like the real deal. This happens millions and millions of times, until the student learns to produce audio that's pretty much indistinguishable from its master teacher, but in a tiny fraction of the time.
And the result? This new parallel wavenet could generate audio more than 20 times faster than real time. This wasn't just a small improvement. This was the fix that finally made WaveNet practical enough for millions of people.
And the quality was backed up by data. In listening tests, people rate the naturalness of audio on a scale of 1 to 5. The old methods? They were stuck in the 3s. But WaveNet scored a 4.21, which closed the gap to actual human speech by over 50%. The difference wasn't just on a chart. You could really, truly hear it.
So, when you put all these brilliant ideas together, you see how synthetic speech went from a quirky lab experiment and landed right in our living rooms, our cars, and our pockets.
And this isn't some far-off future tech. This is the exact technology powering the voice of the Google Assistant right now. Every single time you ask for directions or hear an answer, you are hearing the direct result of this incredible scientific journey.
It's an absolutely amazing achievement, no doubt about it. But it also leaves us with a pretty fascinating and maybe even a little unsettling question for the future. As these voices get better and better, more and more indistinguishable from our own, what happens when we really, truly can no longer tell the difference at all?